Okay, the figure shows in cross-section a central metal ball, 2 spherical metal shells, and 3 spherical Gaussian surfaces. We need to rank the Gaussian surfaces according to the magnitude of the electric field at any point on the surface, greatest first. Here's Gauss's law. Equals the enclosed charge over epsilon naught, and this can pretty quickly become EdA equals the amount of enclosed charge over epsilon naught, which means I can write E as equal to enclosed charge over A epsilon naught. I'm going to look at the first Gaussian surface, which is right here. This Gaussian surface, which has a radius of r, is enclosing this charge, which according to the problem is Q. So here's what I have for the Gaussian surface with a cross-section radius r. This Gaussian surface, it's spherical, it's imaginary, and it appears here as a circle because we're looking at a cross-section of this sphere. So here I have E equals the amount of enclosed charge, which is Q, given in the problem statement, all over the area, which is 4 pi times the radius squared. In this case, that would be r squared. And here's my epsilon naught term. Now I'll look at this Gaussian surface with a radius of 2r. It's enclosing the same Q, but it's also enclosing this charge as well, which is given as 3Q. So for the 2r Gaussian surface, the electric field equals the amount of enclosed charge, which is Q plus 3Q, over the cross-section area, which in this case is 4 pi r squared, but the radius is 2r quantity squared epsilon naught. This becomes 4Q all over, I'll write it like this, 4 times 4 pi r squared epsilon naught. And you can see this reduces down to the same result, Q over 4 pi r squared epsilon naught. Now I'm going to look at this Gaussian surface right here. This Gaussian surface right here has a radius of 3r. It is enclosing this charge, which is Q, this charge, which is 3Q, and this charge, which is 5Q. So here goes for the 3r Gaussian surface. I have the electric field equals Q plus 3Q plus 5Q all over 4 pi r squared, and in this case r is 3r quantity squared epsilon naught, which becomes Q plus 3Q plus 5Q is 9Q all over, I'll write it like this again, 9 times 4 pi r squared epsilon naught, which equals, once again, Q over 4 pi r squared epsilon naught. So each of these surfaces has the same magnitude of the electric field. They all have the same value. I should say, yeah, here, here, and here. Before I leave, make sure you can explain how to go quickly from this statement of Gauss's law to this statement of Gauss's law. E is a constant because the distance anywhere on the imaginary Gaussian sphere is the same to the source charge, and it's the area of a sphere. In this case, it's a Gaussian sphere. Okay, in the figure, an electron, that's a keyword, is released between two infinite non-conducting sheets that are horizontal and have a uniform surface charge density, as indicated. And the question is, rank the magnitudes of the electron's acceleration greatest first. So my natural starting point is, if I need to worry about acceleration, I'm going to remember Newton's second law, which says F equals ma, which means A equals F over m. And I know that F can be represented as Q times E over m. And a little sidebar on that, the definition of electric field is force per charge. So that's how I get force can be expressed as charge times the electric field. And in this case, the electric field can be given, there's my Q over m term. My electric field is in general sigma over epsilon naught. So a little sidebar on that term. The electric field between two plates, the electric field between two non-conducting charge plates is given as surface charge density over epsilon naught. This expression was developed in chapter 22 and then again in chapter 23, and it will reappear in chapter 25. So it's a big deal for some reason, and you will find out why if you don't know why already. So my expression for accelerations, I have to rank them according to accelerations, is going to be Q sigma over m epsilon naught. So let's look at the first situation, situation number 1. The acceleration equals Q, and the Q is the charge of an electron, so I'll just write it down as E, the elementary charge, all over m, that's the mass of an electron, epsilon naught. And now let's worry about this term, the surface charge density term. For situation number 1, they gave you the surface charge density of the positive plate is 4 sigma, and the surface charge density of the negative plate is 4 sigma. Remember that sigma is the charge density or charge per area. So for situation number 1, I have all of these electric field lines flowing into that negative plate, because by convention, electric field lines flow into a negative source charges. Similarly, electric field lines always flow out of a positive source charge. And I think what I'll do is I'll get rid of one of these field lines here. So I'm drawing 4 field lines coming out of that, flowing out of that positive plate, and 4 field lines flowing into that negative plate. And I'm drawing 4 field lines because situation 1 says this is the charge density. Plus 4 sigma for the positive plate, minus 4 sigma for the negative plate. So I'm going to use that number. I'm going to use 4 plus 4, or 8 sigma, for situation number 1. Again, let me just mention that I'm just drawing 4 field lines emanating out from that positive plate. And all I'm doing is worrying about the middle region here. I'm just concerning myself with what's going on between the plates, because that's where the electron is. I don't care what's happening here or here, just what's going on between those plates. Okay, for situation number 2, let's see, I have plus 7 sigma for my positive plate, minus sigma for my negative plate. So let me represent that visually. Plus 7, 1, 2, 3, 4, 5, 6, 7. And for my negative plate, I don't know if I'm being consistent with colors, but for my negative plate, it's just minus sigma there. So when I add up all of these field lines, I have a total of 8 field lines, and that's just meant to be representative. within this region, again, I don't care about up here or down here, I have 8 field lines, which are sort of a proxy for the electric field strength. I have some amount of charge on my negative plate, but I have 7 times that on my positive plate. So I'm going to give this also a value of 1, 2, 3, 4, 5, 6, 7, 8 of 8 sigma for situation number 2. So the acceleration is E times 8 sigma again, not being consistent with colors, but this is just scratch paper, all over m epsilon naught. For situation number 3, I have for the positive plate has a surface charge density of 3 sigma. My negative plate has a surface charge density of -5 sigma. So for the surface charge plate, 1, 2, 3, and for the bottom negatively charged plate, 1, 2, 3, 4, 5. So once again, cumulatively speaking, this is corresponding to once again, this is corresponding to an overall surface charge density that's equivalent to 8 sigma. 3 of the sigmas are coming from this top plate, and 5 of the sigmas are provided by the bottom plate. So cumulative 8. So you can see that I think I have the same acceleration. Acceleration equals E, the elementary charge, times 8 sigma again, all over m epsilon naught. So in every case, the acceleration experienced by this electron right here, is the same in all 3 cases. The figure below shows 4 situations in which 4 very long wires extend into and out of the page. We see only their cross sections. We need to rank these situations according to the magnitude of the net electric field at the central point greatest first. This seems like a job for cylindrical symmetry because wires are basically cylinders. I'm going to draw a surface. I'm going to draw a circle. This circle represents the cross-section of an imaginary Gaussian cylinder that is extending into the page and out of the page. I'm just seeing the circular cross-section. Again, this is my imaginary Gaussian cylinder surface. So for situation A, this imaginary Gaussian surface is enclosing +5. So basically, the enclosed charge, not directly, but kind of indirectly, is +5, enclosed by this imaginary Gaussian surface, which looks like a circle in cross-section. Now I'm going to move this circle over here, and again, I'm sizing it intentionally. I'm sizing it so this point P is on the Gaussian surface. That's always the criteria. That's why you size these surfaces the way you do. This amount of enclosed charge is -5, so I'll just, again, Qn equals -5. And you might say, well, these are charged wires, not charged, but everything else being equal, I can call this +5 for the contribution on the left side, these 2 charges, and I can call this -5. -2 minus 3, -5 over here, and +3 plus 2 is +5 over here. I'll do this again for situation B. Same approach. I'm sizing my imaginary Gaussian surface intentionally. The enclosed charge on that left side is -2 because +2 minus 4 is -2. And if I do the same thing on the right side, the total amount of enclosed charge is -4 minus 2 is also -2, which I'll just write down -2 on this side. Okay, for situation C, I'm going to draw a larger imaginary Gaussian cylinder, and I'm sizing it to enclose those 2 wires, which, again, I'm just thinking of them as charges. and size to include point P. So my total amount of enclosed charge here is positive 8, minus 2, or plus 6. And when I move my circle over here to the right side, size just right to include those charges and have point P sitting on the surface itself, then my amount of enclosed charge over here is plus 10. Last but not least, I'll do the same thing one more time with my bottom situation, which is situation D. The total amount of enclosed charge here is minus 6 plus 5, or minus 1. And on the right side, you can see that it's plus 5 minus 6, or also minus 1. Okay, let me state Gauss's law again in sort of basic form. I will quickly go from this version of Gauss's law to this version of Gauss's law because of the symmetry I have here. EA equals Qn over epsilon naught. Or I could just say the electric field equals the amount of enclosed charge, the charge enclosed by that imaginary Gaussian surface, over A times epsilon naught. My Gaussian surfaces are all imaginary cylinders, cylindrical symmetry, cylinders. I know the area of a cylinder is 2 pi r times the length of the cylinder. 2 pi r is the circular cross-section, L is the length of the cylinder. So now I can say the electric field is going to equal the amount of enclosed charge all over 2 pi r times L. This R value is going to vary from situation to situation. So for situation A, I guess I can say the electric field, I'm just talking about the left side, the electric field is equal to the amount of enclosed charge, which is positive 5, all over 2 pi times R. And in this case, R equals D times L. Let's talk about how R equals D for the situation A. Here's my circle again, which represents the cross-section of my chosen imaginary Gaussian cylinder. And here's where you can see how the radius here is D. It's given as D in the problem statement. On the right side, I have the same circle, the same cylinder. So I can write here on the right side, the electric field also equals negative 5 is my enclosed charge over 2 pi D again times L. I'm not going to include sigma naught, or I'm sorry, epsilon naught, just because it's going to be the same in every case. So rather than drag it along, I'm just going to leave it out because I'm going to do comparisons. So now we have to be careful. On the left side of situation 1, this was a net positive charge that was enclosed by my Gaussian surface. So basically, I have the electric field going, emanating outward, or as far as point P is concerned, I have the electric field going in that direction due to the left side wires. And, you know, that gets doubled. That gets doubled because the right side region, which is the charge enclosed by this circle, has a net negative charge. So they kind of double. They have this reinforcing effect. So this is how I'm going to record the situation A. Situation A has a net, I'll just write it as 10. Positive 10 over 2 pi dl, and I probably don't need to drag along some of this stuff, but that 10 comes from 5 here and then another 5 here, and you have to be aware of direction. This 5 means the electric field lines are flowing this way, and this negative 5 means this electric field, due to these source charges, are also flowing towards the right. So that's why I'm calling that 10. So let me pick up the pace. For situation number 2, it's going to equal, due to the left side, E equals negative 2, looking here, negative 2 all over 2 pi dl. And on the right side, that's also a negative 2. Negative 2 over 2 pi dl, not dragging along the epsilon naught. And now we have to look at what's going on with the field lines. In this case, I guess I'll use this color for field lines. The field lines, let's see, this is a negative source charge negative region. So the field lines are flowing this way due to positive 2 and negative 4. And similarly, they're flowing this way because this is also a negative region. Electric field lines flow into a negative region, and I have a negative region on the left and a negative region on the right. So in this case, I get a perfect canceling of electric fields. So for situation B, I'm just going to write that down as 0. Okay, for situation C, there's my imaginary Gaussian cylinder once again. I have to worry about the radius of this Gaussian surface. So this is D, and this is 2D. So the center of this circle has a radius of 1.5D. So 1.5D is the diameter for this particular imaginary Gaussian cylindrical surface. Okay, so for the left side of situation C, I have the electric field equals the enclosed charge, and the enclosed charge is that plus 6 all over 2 pi times the radius of that imaginary Gaussian cylindrical surface, or 1.5D times L. On the right side, I have E equals, and the total amount of enclosed charge is plus 10 all over same cylindrical surface, same imaginary Gaussian cylindrical surface. So this would be 2 pi 1.5D times L. So I have to worry about direction. Let's see, on the left side here, this is a positive region. So the field lines are going to be flowing out of a positive region. So the arrow looks like that at point P. On the right side, this is also a positive region. So this arrow is going to be flowing this way. So you get sort of this cancellation effect. So I have 6 over here flowing to the right, 10 over here flowing to the left. So that's going to net out to 4. So let me write that down. So this will be 4 all over 2 pi times 1.5D times L. I play this game one more time with situation D, and let me maybe try to do a bit of redrawing because things are pretty messy. The radius of my imaginary cylindrical Gaussian surface is 1.5D because this is D, this is D, and this is D. The left side in situation D is a negative, so as far as point P is concerned, the electric field is going to be flowing that way to the left. So E equals the total amount of charge, enclosed charge, which is negative 1, all over 2 pi times 1.5D times L. On the right side, E equals the total amount of enclosed charge, which is also negative 1, all over 2 pi times 1.5 dl. Because the right side of situation D is also a negative region, I have the field line going in this direction, so they cancel. I don't have to do any thinking, really. The net electric field for situation D is also equal to 0. So let's start adding things up. Let's see. For situation B, the net electric field is 0. For situation D, the net electric field at that point is also 0. For situation A, if I simplify that down, I have 10 over 2 pi, or maybe just 5 over pi dl. And for situation C, I have 4/3 all over pi dl. Let me make things clear and just repeat one more time and sanity check. Situation B and D produce no electric field at point P because you have that destructive interference, that cancellation. Situation A, I have 10 over 2 pi dl, which is why I'm saying this is 5 over pi dl. Situation C, I have 4 over 2 pi 1.5 dl, which is why I'm calling this 4/3 over pi dl. So as far as the rankings are concerned, the electric field at point P in situation A is greater than situation C, and situation C is greater than situation B, which is equal to D because B and D are both 0.